Now let's look at another graphing problem. We want to graph f of x equals 3 to the x power. To accomplish this, we're going to use plotting points, and we're just going to take some values that are integer values. Let's just use -2, -1, 0, 1, 2, and evaluate. Now, we have to remember properties of exponents in order to evaluate here. For instance, let's recall that if we have 3 raised to the -2 power, that is going to be equivalent to 1 over 3 squared, which is going to equal then 1/9. So for the value of x equal to -2, our y value will be 1/9. What happens if our exponent is -1? 3 to the -1 power is equal to 1 over 3 to the first power, which is just 3, so we end up with 1/3. What about 3 to the 0 power? You'll recall that a number 3 raised to the 0 power gives us the value of 1. 3 to the first power is 3, and 3 to the second power is 9. Now let's graph these points. Notice one thing is that all of our values for y are going to be positive, and that's because as we raise a positive number to a power, we always end up with a positive result. Here I'm going to label positive 1, positive 2, positive 3 as we move to the right, and -1, -2, -3 as we move to the left. And then we're going to move upward. Let's just use smaller units. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then here's 10. Let's plot some points. We have -2, 1/9. Now, -2 is 2 units to the left. 1/9 is going to be very close to the x-axis without touching. -1, 1/3. We're going to move just slightly upward. It's very hard to tell that we've moved up here because it's so slight. 0, 1, we're going to be on the y-axis, 1 unit up. 1, 3, we're going to be over 1 and up 3 units. And 2, 9, over 2 units and up 9. Now, we're going to connect these dots with a smooth curve. We can see that as we increase toward the right, we would end up getting a rapid increase with our y value. So an increase in x is going to be a corresponding increase in y. As we move to the left, we're never going to cross the x-axis. It would get closer and closer and closer without ever touching, and yet that ends up giving us something that's going to be called a horizontal asymptote. In our next problem, we're going to compare linear models and exponential models. Use the following functions and table to solve this problem. F of x equals 0.074x plus 2.287, and g of x equals 2.566 times 1.017 to the x power, where f of x and g of x equal the world population in billions, and x is equal to the number of years after 1949. The actual number of years after 1949 and world population are given in this table of values. First problem we want to look at. World population in 2000 was 6.1 billion. How well do the functions model world population for that year? Well, what we're looking at are the number of years after 1949. So in the year 2000, our x value is going to be 51. So we're going to have f of 51, which would equal 0.074 multiplied times 51 plus 2.287. Using our calculator, we would multiply first and then add to give us f of 51 equals 6.061. G of 51 is going to be evaluated by taking 2.566 and then taking the value of 1.017 and raising that to the 51st power. Again, using our calculators, we'd raise to the 51st power and then multiply by the 2.566 to come up with a value of 6.062 approximately. And now if we round that to the nearest tenth, we can see that in both cases we end up with approximately 6.1 billion, which fits that. By one projection, world population is expected to reach 7 billion by 2012. Which function serves as a better model for this prediction? We can take in 2012, that would be 63 years after the year 1949. So we'll have f of 63, which will be evaluated 0.074 multiplied times 63 plus 2.287, and that is approximately 6.949. And then if we find g of 63, that's going to equal 2.566 multiplied times 1.017 raised to the 63rd power, and that is approximately 7.421. Now, we said that the world population would be expected to reach 7 billion. We can see that, approximating even further, the 7 billion is closer to the linear model than it is to the exponential model, which would round to 7.4, as opposed to this rounding to 7.0 if we go to the nearest tenth. Here's another application problem. Medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. The risk is modeled by the formula R equals 6 times e to the 12.77 x power, where x is the blood alcohol concentration and R, given as a percent, is the risk of having a car accident. In many states, it is illegal for drivers under 21 years old to drive with a blood alcohol concentration at 0.01 or greater. What is the risk of a car accident with a blood alcohol concentration at 0.01? And then round to 1 decimal place when we find the result. Well, let's repeat this function and make sure we understand each part of it. We have R, which stands for the percent, and that's going to be equal to the number 6 multiplied times the number e. Now, you should be familiar with the number e. It's a value that's approximately equal to 2.7. It is a constant. We're going to be raising that to the 12.77 times x power. So this is going to be the exponent power that we raise the value e to. In this problem, we're trying to figure out the relationship between the risk of a car accident with the blood alcohol concentration. We're told that the value of x is equal to the blood alcohol concentration. And at the bottom, we want to find that risk when we are given the value of x equal to 0.01. Let's evaluate this by substitution. We'll have R equals 6 times e to the 12.77 multiplied times 0.01. Now, in order to evaluate this, remember that we have to find that exponent first before we would raise to the power. We can do this completely on a calculator as long as we're assured of putting the exponent in parentheses. If we do a little bit of this by hand, to demonstrate, we're going to have R equals 6 times e. We're going to multiply 12.77 times 100th, and that gives us our exponent of 0.1277. Now, using a calculator, we can come up with our value of R. And substituting in to our calculator, we would have 6 multiplied times e raised to the 0.1277 power. We come up with an approximate value of R as 6.8. We'll interpret this by understanding that our R stood for a percent, and so this would be a 6.8% chance of having a car accident with this blood alcohol concentration. Now let's look at graphing a logarithmic function. Rewrite y equals log base 2 of x in exponential form, then use the exponential form of the equation to obtain the function's graph. Select integers from -2 to 2 inclusive for y. We're going to have our equation, which is logarithmic. We want to change that to its exponential form. Now, we read this y equals log base 2 of x. The base in the exponential form will be the value of 2. A logarithm is equal to an exponent, so we're going to have our exponent equal to y, and this will equal the value of x. We're asked to come up with a value for y, between -2 and 2, and we're going to substitute into this equation. So we have -2, -1, 0, 1, 2. As we substitute for y, we're going to be able to evaluate x. So 2 to the -2 power, recall, is going to equal 1 over 2 squared, which is going to be 1/4. 2 to the -1 power will be 1 over 2 to the first, which is 1/2. 2 to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. And now we're going to graph these points. So let's plot 1, 2, 3, 4 units on the x-axis, do a couple of marks on the y-axis, and let's go ahead and graph. We have x equals 1/4, y equals -2. Now that's moving a quarter of the way to the first unit and then down 2 units. We then have 1/2, -1, move halfway and then down 1. We have 1, 0 on the x-axis. We have the point 2, 1. And then we have the point 4, 2. Now we'll connect these values with a smooth curve. Now, if we think about it, notice that our x value is equal to 2, a positive number raised to a power. Our x value will always be something that's positive. And for that reason, we see that our graph is only in quadrants 1 and 4. Now let's look at an application where we use a logarithmic function. The function f of x equals -11.6 plus 13.4 times the natural log of x models the temperature increase, f of x, in degrees Fahrenheit after x minutes in an enclosed vehicle. Find the temperature increase to the nearest degree after 30 minutes. And then, once we find that answer, we'll answer the question as to how well the function models the actual increase of 34 degrees. To use a function like this, we have to make sure we understand what we're substituting for. The x value in the function stands for the number of minutes after we've been in an enclosed vehicle. So to find the temperature increase to the nearest degree after 30 minutes, we recognize that all we have to do is to evaluate f of 30. Now that requires us to rewrite the function -11.6 plus 13.4 times the natural log, this time substituting in our value of 30. Using your calculator, you can substitute this expression in and find out that f of 30 is approximately equal to 34. And since we're now being asked to determine whether the function models the actual increase of 34 degrees, it turns out it's a very good model indeed. Now let's see the process for graphing a quadratic function. Graph the quadratic function y equals x squared plus 6x plus 5. Step 1, determine how the parabola opens. The parabola opening is determined by the coefficient of x squared. If our a value is greater than 0, we're going to have a parabola which opens upward. If our a value is less than 0, we're going to have a parabola which opens downward. We can look at our example and see that our coefficient in front of x squared would be equal to 1, which is a positive value, so we know that our parabola will open upward. Step 2, find the vertex. We'll use the formula x equals -b divided by 2a. In our example, our a value is equal to 1, and our b value is equal to 6. So we substitute to get -6 divided by 2 times 1, which is equal to -3. To find the y value, we go back to the equation and we substitute. Y equals -3 squared plus 6 times -3 plus 5. -3 squared is 9. We'll multiply here to get -18. 9 minus 18 is -9, plus 5 is going to be -4, giving us our vertex with coordinates -3, -4. Now we want to, in step 3, find the x-intercepts. If it's going to be an x-intercept, that means it lies right on the x-axis. which indicates that our y value must equal 0. So we're going to have our equation where we substitute 0 in for our y, and we're going to then look at the quadratic equation. 0 equals x squared plus 6x plus 5. We can use factorization to solve this. Factors of 5 are 5 and 1. Now let's set each factor equal to 0. X plus 5 equals 0, or x plus 1 equals 0. That gives us our x-intercepts, which will be at -1 and at -5. Now let's look at step 4. Step 4 would be to find the y-intercept. Our equation again was y equals x squared plus 6x plus 5. If we're finding the y-intercept, that means that our x value must be 0. So we'll evaluate y equals 0 squared plus 6 times 0 plus 5, which is equal to 5. Steps 5 and 6, let's plot the intercepts in the vertex and connect these points with a smooth curve. So we'll quickly sketch out our axes. And let's mark some units. 1, 2, 3, 4, 5 in each direction. And plot our points. We had our vertex at -3, -4. Moving 3 units to the left, 1, 2, 3, and 4 units down, 1, 2, 3, 4, we can plot our vertex. Now we had our x-intercepts. Recall that our x-intercepts were -5 and -1. So we're going to have a point on the x-axis 5 units to the left and another point 1 unit to the left. Our y-intercept had a value of 5. So we'll be 5 units up on the y-axis. Now we know that this has a parabolic shape. We're going to also note that we have symmetry to the graph, so we're going to connect it, making it look like a U, going upward here, and same shape over here, and there we have our graph. In our next problem, we're going to use a model to determine some values for a given application. Use the model f of x equals 4,000ths x squared minus 94,000ths x plus 2 and 607,000ths, where if f of x is U.S. wine consumption in gallons per person, and x is the number of years after 1980, to determine U.S. wine consumption in 1995. How well does this describe the value shown by the following bar graph? Well, in the bar graph, we can see that in the year 1995, we're looking at a value of 2.1 gallons per person. The equation that we're going to be using requires us to know the value for x, which will be 15 in this case, as 1995 is 15 years after the year 1980. So substituting the value of 15 will look like this. We'll have our 0.004 multiplied times 15 squared minus 0.094 multiplied times 15 plus 2.607. Now you may be using a graphing calculator, in which case you can enter this into the graphing calculator as it stands. If you're using a scientific calculator, you'll probably have to use order of operations in order to get the correct result. F of 15 in either case is approximately equal to 2.1. F of 15 is approximately 2.1 gallons per person, which is very accurate according to the bar graph.